Hello, and welcome to Lesson 5 of this Introduction to Calculus with Wolfram U. Our topic for today is the laws of limits. So let's begin with a brief overview of today's lesson. So we learned in the previous lesson that using tables to find limits can be very tedious work. So what we do today is to set up some laws for limits which will let us compute the same limits quite easily. And to do that, I'm going to use two example functions. The first one is called f, the second one is called g. So f is 2x plus 2 and g is 3 times cosine x over 2. So those two functions are going to serve as our example functions in the first part of the lesson. So here are the plots of the functions. F is of course just a linear function while g is a trigonometric function. Now, if you look at the plots, it's clear that the limit of f is going to be 2 at 0, and the limit of g is going to be 3 over 2. So let's confirm that with the limit function. The limits are 2 and 3 over 2. So you'll need to bear in mind throughout today that f is this linear function, g is a trigonometric function, and the limits are 2 and 3 over 2. And with just that small piece of baggage, we can now begin our discussion of the laws of limits. And the first law is called the sum law. It says that the limit of a sum is the sum of the limits. So for example, if you want to find the limit of f plus g, you simply add 2 and 3 over 2 and get 7 over 2. And you can check that with the limit function and get back just the same result. So here's a plot of all three functions, f, g, and f plus g, and you can see quite clearly that f plus g, which is right over here, has got the limit 7 over 2 as x approaches 0. Now, along with that, you can also say that the limit of a difference is going to be the difference of the limits. So in our case, it's going to be 2 minus 3 over 2, that's 1/2. And you also have a scalar multiplication law, which lets you multiply a constant by a function, and then you simply do the limit of the function times that constant. So if you want to find the limit of 3 times f of x, it's just going to be 3 times the limit of f of x. So it's 3 times 2 is 6 in this case. So you got the sum law, the difference law, and the scalar multiplication law so far. And to go on, let's talk now about the product law, which says that the limit of a product is the product of the limits. So for example, if you want to find the limit of f times g, it's just going to be 2 times 3 over 2, that's 3. And you can check that with limit and get back just the same answer. So here's a plot of all the three functions, f, g, and f times g, and you can see quite clearly that the limit of f times g is 3, exactly as we said early on. And along with the product law, we also have the power law, which says that if you want to find a limit for power, then it is the power of the limit. So for example, the limit of f cube is the cube of the limit of f. So 2 cube is 8, and therefore you get back 8 as the answer. So now you got the sum law, the difference law, the scalar multiplication law, the product law, and the power law. And as a next law for us, we take up the quotient law. So when you divide, things can go wrong, but most of the time they don't. So the limit of a quotient is the quotient of the limits, provided that the denominator does not have a limit of 0. So in our case, f and g, you have the limit of f over g is just 4/3, because 2 over 3 over 2 is 4/3. So here is a plot of all the three functions, f, g, and f over g, and you can again see what's happening, that the answer is actually correct as guessed by us. There is a problem at pi over 2 although, because the value of g at pi over 2 is 0. And then we are in trouble because the limit of f over g at that point is just indeterminate. So the quotient law is almost true, and it's not true when the denominator is becoming 0 in any way. Okay, so some examples now of limits. So if you have a polynomial, then you can quite easily compute its limit. But to do that, we need to accept some facts. So first of all, fact 1, the limit of a constant is a constant. So let's check that. So the limit of 5 would be 5, and the limit of 1/2 would be 1/2, etc. So the limit of a constant is a constant. And the other fact is that the limit of the simple function x as x approaches a is just a. So you just plug in a and get back the answer. Okay, once you have just those two facts, then you can work out the limit of any polynomial. So for example, if you want to work out the limit of 2x squared minus 4x plus 3, you simply plug in the values over there and you get back the answer at 4, for example. Okay, so we now worked out the limit of a polynomial by substitution. The question is, what happens when you have a rational function? So here is a rational function, and you want to find the limit of this function when x approaches -2. Now, when x is -2, there's no problem at all because the denominator is not 0. So here you have g is the numerator, h is the denominator of the rational function, and to find the limit of f as x approaches -2, you simply divide the limits of numerator and denominator, and you get back the answer 10/13, whether you work out the limit directly or you work it out by taking a quotient, like over here, or you simply work out the value of the function at -2. So rational functions are almost as easy as polynomials in most cases. But to go on, I'll give an example where things can go wrong. So here's an example of a rational function, but you want to find the limit at -1, and sure enough, there's an issue over here because the denominator becomes 0. So denominator 0 over here, we cannot use a direct computation. So what we do is we factor the numerator and check that in fact we have a common factor of 1 plus x. And to cancel this common factor, we can use several functions. I'll use simplify over here, and that will get the function down to its simplest possible form, in which you can plug in the values, and you can see quite clearly that the limit is -1 minus 1, that's -2, and that's confirmed by the limit function. Okay, so that's about rational functions, and now to go a step further, let's talk about difference quotients, which are very closely related to all the previous ideas. So here is the difference quotient for a rational function, and what you see over here is that if you plot it, then it's just a straight line. So what's happening? Well, what's happening is that although the h over here is 0 at h equals 0, there is a common factor, and to find the common factor, you can do an expansion and then do a kind of factoring and get the function down to its simplest possible form. So that function over there, f, which looked difficult, is in fact just 4 plus h. And then what you can do is you can work out the limit of f as h approaches 0 and get the answer as 4. So we've learned now that sometimes cancelling factors is a really good idea. Okay, next, how about things like the absolute value function? So here's the absolute value function. If I plot it, it's kind of got a V shaped. And when you are at 0 over here, then it's clear that the limit is 0, whether you approach from the left or the right. So the left-hand limit and the right-hand limit are both 0 from this picture. And you can confirm that with limit itself by doing a direction computation. So you get back 0 and 0, whether you go from the left or right, and limit itself also gives you 0, so there's no problem over here. So although you do have a kind of piecewise function, it in fact has a very simple limit at 0. On the other hand, here's an example where things can go wrong. So if you divide the real absolute value of x by x, then the plot shows that you clearly have a kind of jump over here. Because when you're to the right, the answer is 1, and when you're to the left, the answer is -1. So the left-hand limit is -1, the right-hand limit is +1, and hence the limit does not exist. So that's a jump at a single point. But of course, things can get much worse. So here is the so-called floor function. So the floor function will calculate the greatest integer less than or equal to x. And the problem is to find where the limit does not exist in the range from -2 to 2. So here's a plot, and it's clear that you have an issue at all the integers. There's a jump at every place. So for example, at 0, you have the left-hand limit is -1, and the right-hand limit is 0, so the limit does not exist. And in fact, you can confirm that at every integer between -2 and 2, you have no limit existing. So all the limits are indeterminate. So the floor function is an example of a function which has no limit at an infinite number of points. Now, in practice, if you have a very complicated function like the one over here, then what you can try and do is to kind of squeeze the function between two simpler functions. So a little more abstractly, if you have a function g, and that function g lies between f and h, and you know the limits of both f and h, then you also know the limit of g. So with the function over here, you can see quite clearly that the cosine is going to go between -1 and 1. So you could pick f to be x square and pick h to be -x square. That's going between -1 and +1. So you got f, you got g, and you got h. G is the complicated one. And if you plot them, you see that g is tightly squeezed between f and h near 0. So g is this wiggly function over here, and it's very tightly squeezed. So the Squeeze theorem says that you can work out the limit of g provided that you can find the limits of f and h. But f and h are simple. They are polynomials, so their limits are just 0, and hence the limit of g is 0 as well. Okay, so that brings me to the end of today's lesson, and I'll summarize by saying that the limit laws give us a way to find the limits of functions mathematically. So you can use tables for sure, but the limit laws are the best way to get the limits of functions. And there are laws for sums, for differences, for products, and for quotients. Now from these laws, you can work out the law of find limits for any polynomial. That's really simple, but it is somewhat harder to find the limits of rational functions, which can become 0 in the denominator at some points, or piecewise functions where things can go quite wrong, etc. And finally, the Squeeze theorem is a great way to find limits when you're given difficult functions which can be squeezed between simpler functions. So this is about today's lesson, and the next lesson will cover continuous functions, which will make life much easier for us as far as finding limits are concerned. But before that, we will have a problem session to discuss various problems which relate to the material covered so far. So do review today's lesson, go over the examples, the exercises, and try and figure out how you might proceed by trying things on your own and mastering the area. So thank you very much, and I'll stop here.